Dissolving regular table salt in water produces a clear, predictable liquid. But dissolving certain metals from the center of the periodic table results in something else entirely. You get intensely colored, swirling liquid chemical solutions of bright blues, deep purples, and vivid yellows. These metals belong to the D block of the periodic table. When they interact with other molecules, standard chemical rules regarding simple ionic bonds are insufficient to describe their behavior. Consider a single ion of cobalt. Depending on the molecules nearby, that cobalt ion can take on a completely different three-dimensional shape. It can switch from being non-magnetic to highly magnetic, or shift its color from pale pink to brilliant blue. This is the science of coordination chemistry. Transition metals act as central hubs, and their properties are governed by the specific molecules, or ligands, that dock around them. As these ligands dock, they actively restructure the metal's internal electronic architecture. Every coordination complex begins with a central metal cation. Surrounding it are ligands, chemical species like water or ammonia that donate a pair of electrons to the metal to form a coordinate bond. Because these ligands carry negatively charged electrons, they repel one another. To minimize this repulsion, they arrange themselves into precise geometric patterns. A metal bonding with 6 ligands typically forms an octahedral layout. If it bonds with 4, it may settle into a flat, square planar framework. This rigid geometry enables isomerism. This is a phenomenon where two complexes have identical chemical ingredients, but those ingredients occupy different positions in three-dimensional space. This diagram shows a platinum central atom bonded to 2 ammonia and 2 chlorine ligands. In the cis isomer on the left, the chlorine atoms sit next to each other. In the trans isomer on the right, they are placed on opposite sides. Even with an identical chemical formula, the physical distance between those chlorine atoms changes the compound's reactivity. The orientation itself dictates how the molecule behaves. This spatial layout serves as the blueprint for the complex, influencing all other properties, from magnetism to color. To understand how these complexes become magnetic, we look at the mechanics of crystal field theory. The metal at the center has electrons located in zones called d-orbitals. As negatively charged ligands approach the metal hub, their charge pushes against the metal's existing electrons. Figure 5.1 illustrates the result of this repulsion. The metal's 5 d-orbitals, which originally shared the same energy level, split apart into 2 distinct sets, a lower set of 3 orbitals and an upper set of 2. When a ligand has a weak charge, the energy gap between these sets remains small. Electrons naturally repel each other, so instead of pairing up in the lower orbitals, they cross the small gap to occupy all 5. Because these electrons remain unpaired, their magnetic fields combine, creating a highly magnetic or high-spin complex. If the approaching ligand is strong, it creates a massive energy gap between the orbital levels. The jump to the upper level becomes too high to cross. Electrons are forced to pair up in the lower orbitals instead. When 2 electrons pair, they spin in opposite directions, causing their magnetic fields to cancel out and neutralizing the magnetism of the complex. For transition metals, magnetism is a conditional state that is dictated by the strength of the surrounding ligand field. The size of that energy gap also determines the complex's color. The gap between the split d orbitals corresponds to the energy of specific wavelengths of visible light. When light hits the complex, an electron in the lower orbital absorbs an incoming photon that matches the energy of the gap. The electron uses that energy to leap to the higher orbital set in a d-d transition. Because a specific wavelength was absorbed to make that jump, our eyes see the complementary color from the light that remains. Potassium permanganate, for example, produces an intensely vibrant purple. However, the manganese ion at its center has 0 d electrons available to make an orbital jump. Stopover 24 explains this through a secondary mechanism called charge transfer. Rather than jumping between split orbitals, an electron leaps from the surrounding oxygen ligands directly onto the manganese ion, creating that intense purple color. The vibrant, swirling color of a metal complex is a direct visual receipt of its internal energy state. Coordination compounds are tunable atomic systems. By swapping an attached ligand, we can alter the metal's physical shape, its magnetism, and its absorption of light. This coordination allows hemoglobin to transport life-sustaining gases. The iron complex at the protein center adjusts its electronic configuration to lock onto oxygen in high-pressure lungs and release it in oxygen-depleted tissues. Geometry remains a critical factor in modern medicine. The platinum compound cisplatin is an effective anti-cancer drug because its specific cis orientation allows it to bind to DNA and prevent cancer cells from dividing. Its identical trans isomer cannot form that connection. Coordination chemistry provides a control panel for molecular behavior. By selecting specific ligands, we can dictate how a metal binds to a DNA strand or how a catalyst initiates a specific chemical reaction.